hopefully below a minute or two. So Dr. Folley has completed his PhD in the design of wave energy converters at Lancaster University back in 1991, and he was incorporated into Queen's University, Belfast in the early 2000s. He has seen, and he's got great expertise and seen the large changes in the wave energy industry, from small academic research efforts to the current emerging industry that we all know. He has been at the forefront of wave energy for many years. I was lucky enough to have him as a visiting lecturer, so I'm very happy that he took his time to do this presentation. Dr. Folley has been actively involved in several stages of development processes for wave energy converters, including both the assessment and also the introduction of novel concepts. He has over 60, 70, if I'm mistaken, you can correct me, scientific publications in the field of wave energy, and has worked with key industrial players in several projects that have been a milestone in the wave energy industry. He has worked with some companies, namely Wavegen, and all of you know the LIMPET wave energy plant, and of course Aquamarine wave power with the Oyster converter. Matt is currently, amongst his other functions, a vice chair of the WECANET Cost Action, which is a pan-European network for marine renewable energies with a focus on wave energy. He is the chair of the IEC Technical Committee on developing international standards for marine wave energy converters and assessments. And he is the UK principal expert on the IEC committee for the performance of wave energy converters. So this is in brief. I give the floor to Dr. Folley. And if I've missed anything, please. So enjoy.
No, that's great. Thanks, George. That's a nice introduction. Makes me feel quite old when you talk about a PhD back in 1990. But there we go. Maybe I'm older than I think. So what I wanted to talk today about is a new sort of type of wave energy converter, which we've started working on, which is based on lift type forces. Now, what I want to do in the presentation is sort of take you a little bit through the reasoning about why we wanted to investigate this particular area and how we're getting on in the research in this area, and hopefully encourage you to think about wave energy in a deeper way than perhaps it's possible. So this is quite a brutal slide, and what I'm trying to say here is, if you look at the commercialization of wave energy, it's not been successful. We had three technologies there: LIMPET, Polaris, and Oyster. Probably between them, they've had 100 or 200 million euros invested in them, and they're all now defunct. They're all no longer sort of considered to be commercial. At least the companies developed them have gone into receivership. And I think, to my view, that means that we need to review what we're doing and whether we're heading in the right direction. Now, companies will become unsuccessful or go into receivership for lots of different reasons. It's not necessarily the fundamental technology which is an issue, but it makes sense, if we're honest with ourselves, to say, what reasons could there be, and what other avenues are there available to look at the potential for exploitation of wave energy? Because what I don't want to say is I think wave energy, there's no hope, but what I'm trying to look at is other areas of wave energy, or how we can look at wave energy in a different light in order to move forward, to try and make a commercial success of wave energy. What's interesting, when you start to look at the development of new ideas, you find there's a massive amount of inertia and sort of disincentivization of moving forward with new ideas. And so often you find that someone comes up with a new idea and it's considered wrong for all sorts of reasons, whether it's prejudice or commercial interests. But essentially, normally a new idea actually is considered to be a bad idea when it first start. So often you'll say, I've got this new idea, and people say that won't work for X reason, Y reason, or Z reason. And so I think the question is, you've got to investigate why those views are held and whether those views are reasonably held. You know, whether it's reasonable to hold the view that, okay, this new idea that's come up is an idea which genuinely doesn't appear to have much potential, whether it's just a prejudice or a perspective which we're having on the idea which makes us think that way. So one way to look at ideas or new ideas in wave energy, at least, is look at how they couple with the waves. Now, clearly, to extract energy from the waves, we need to couple with the waves in one way or another. So we need to extract the energy from the wave, which is mechanical, and extract that mechanical energy into normally electrical energy to generate electricity. And so therefore we need to create a force. Now, because the wave particles are moving, they all instances they have a displacement, a velocity, and acceleration. So you can think about the waves or coupling with the waves in those three terms. You can think of them coupling with the buoyancy or displacement, velocity, which is lift, which is the one which I'm going to focus on in this presentation, or acceleration, which is a diffraction force. So the first thing to look at the ideas is to say, let's have a look at what ideas have been investigated so far in wave energy from a commercial perspective. So what I tried to do is look at all the devices which have had a reasonable amount of commercial investment. So there's a reasonable amount of effort been put into these technologies. And you'll see that lots of devices based on buoyancy have been proposed and developed. A relatively large number have also used diffraction, but very, very few have used lift forces. And of course, there are some which may be a little bit difficult to put into this classification. Some perhaps use more than one type of coupling, that they also couple both with displacement and acceleration, or both with buoyancy and diffraction. But in general, the point is that very, very little or very few technologies have been proposed and developed from a commercial perspective that look at lift. If we then go on to the academic perspective, if you sort of went back through all the papers that have been written on wave energy since about the 1970s, when the rebirth of wave energy, serious wave energy started, there's been thousands of papers that have looked at the effect of, or the coupling of waves with buoyancy or displacement. So there'll be oscillating water columns, heaving buoys, all fit into that sort of primary coupling with the wave. And then also probably thousands on diffraction, where, if you like, the archetypal type thing will be a flap, where we have the effect of acceleration on the flap and diffraction, that creates a force. If you then started to search for papers which looked at the coupling with lift, there's probably only tens of papers. As part of the research program that we're doing now, we did a fairly extensive review of these exploitation lift for wave energy conversion. And I think we probably identified 25 different papers. And so when you compare the sort of effort that's gone into these three different fundamental ways of coupling with the waves, you can immediately identify that lift has had significantly less research into it than the other forms of coupling with the waves in terms of extracting energy. And just as a very concrete example, I went through the UTEC 2019 papers, the European Wave and Tidal Energy Conference, which is the world's sort of leading academic conference for wave energy. And I found 44 papers which were talking about the coupling with buoyancy. 9 papers looked at the coupling with diffraction. And only one paper, which was actually the paper I presented myself, which looked at the coupling of lift or velocity with wave energy. So if you're looking at a research area, you can see that there's significantly less research and less effort and less focus gone on lift-based devices than other types of devices. So if we were to look at looking for new ideas, and what I've done here is shown the 3 different types of fundamental ways that you could couple, and I've shown some overlap because certain technologies will overlap with each other. And if I looked at the current area of research, it really covers buoyancy and diffraction quite significantly, but only just touches the use of lift for wave energy converters. And what I really feel we should do is move that area of research to include lift. So we're looking at lift as a potential viable way of generating energy from the waves. So let's have a look at the sort of things, knowledge that we really want to know in terms of wave energy. So we want to know what the hydrodynamics of lift-based wave energy converters are. So how do they work? You know, how do we couple with the velocity of a wave in order to extract energy? How should we control it in order to maximize that energy? If you look at the current literature, it's very well understood what the optimal control of other types of wave energy converters based on diffraction and buoyancy. We now know to a very good degree how they should be controlled, but how should we control lift-based wave energy converters in order to maximize their performance? So what's the optimal design of a lift-based wave energy converter? How big should the hydrofoils, indeed if we decide to use hydrofoils, how big should they be? Are they better deployed in deep water or in shallow water? Should we have one hydrofoil or two hydrofoils or 10 hydrofoils? And obviously the last question is critical, is there a commercial potential associated with this type of coupling with the waves? So can it be done economically? Do we think there's reasons to believe that it can be done, or there are commercial potential for this type of technology? And if we go through these, I've sort of said, well, you know, if you look at the research literature, there has been some work done on hydrodynamics by Atargis, the company which is developing the slight quake technology. But they focused on their technology, understandably, because that's what they're trying to do. So we need further research in all of these areas. Indeed, it could be argued that some of these areas have really not been investigated. So if we looked at the optimal design, SiteQuake have said this is what we believe the optimal design is. But obviously, as a commercial company, you know, it's not really in their interest, especially to explain why they feel that design is better than other design. That's a commercial perspective. And obviously what we need to do, or what needs to be done, is to develop some support for that from an independent perspective. So it's not just the company that's saying, we think this is good. There's some independent academic research which is able to support or qualify their perspectives. And so this is where I believe, you know, we need to go. Now, lift-based wave energy converters, I've sort of talked about this in a variety of conferences, mostly in the sort of social areas, to sort of sound out people's views. And normally when people are relaxed and quite comfortable, they know me quite well, they'll often say, no, I can't see wave energy based on lift forces working. I say that's fine. I don't have a problem with them having that view. Everybody has to have a view, or everybody should have a view in what they think will work and what won't work. The interesting thing is, if I then ask them, why do you hold that view? There'll be a variety of reasons, or a variety of things given for why they hold that view, but actually the evidence used to support that view is very, very scarce. And so what happens is we end up basing it on perceptions and prejudices. And I mean prejudices not in a particularly negative sense, but we're prejudging how we think a lift-based wave energy converter will work because the research hasn't been done. So this is where I start from, is that we need to do the research, we need to do development to understand whether this type of technology has potential. How is it relative to the other types of coupling with wave energy? And so therefore, you know, where should we go and how can we move forward? Now, I've talked relatively abstractly about a lift-based wave energy converter. And I've done that deliberately because I don't want to constrain people's views on what they should be. But I also recognize that it's useful to have a sort of something to envisage. So here I've created an animation of a device which just shows one instance of how you could couple. Here they're using hydrofoils, and it moves around with the wave at the same frequency as the waves. So that's, and it uses two hydrofoils. The point I want to make here is that whilst this is one implementation, it's not the only implementation. So we shouldn't get sort of too focused on this particular instance, this particular concept, but it can provide an example for people to understand, or at least sort of link what I'm going to talk about next. So let's have a look at what advantages or what potential we could have on lift-based wave energy converters. And I think there are two advantages which are worth highlighting, because they're different to some extent from other wave energy ways of coupling with the waves. They're different from buoyancy and diffraction forces. So the first one is that the lift force is controllable because it's proportional to circulation. And so what we would have in a wind turbine is, the way wind turbines work is when the wind gets too strong, they turn the blades of the wind turbine so they don't generate circulation anymore. And the advantage of that is that you then take away the largest load. So however you want to extract energy, you need to have a load and a velocity. You need force and velocity. So we want high forces when it's operating. You can't avoid that. That's a fundamental requirement. What you don't want is those large forces. You want those large forces to disappear when you get to very large waves where the main purpose is survival. And the nice thing about lift-type devices is that it's relatively easy, by removing the circulation, to reduce that lift force, in the same way that wind turbines reduce that thrust from the wind by feathering the blades into the direction of the wind. So we have an advantage, if you like, in terms of the controllability, especially in terms of survivability. The other advantage is that we have it's potential to have unidirectional rotation. So you can see in that animation that the thing is turning in one direction. And the advantage of that is that we avoid oscillating loads on the drivetrain. So if you look at a heaving buoy, for example, twice every wave cycle, the velocity stops and then changes direction. And so you get these oscillating loads on the drivetrain, which you've then got to deal with. And you've got to think about, how do I extract the energy most efficiently? And so you end up quite often with hydraulic systems or some way of converting it into electricity, which is efficient. Of course, with unidirectional rotation, we can theoretically directly couple to an electrical generator. And so we have a lot more familiarity, let's say, with that type of generator. Now, of course, if you're directly coupling with the electrical generator, you're turning at the same frequency as the waves, which is about 6 RPM, 8 RPM, depending on your wave climate. And that's very low relative to a normal generator. And so the first question is that too low to be viable? Is it just too low for us to work with? If you look at modern wind turbines, the very large ones, the 8 megawatt turbines, 10 megawatt turbines, they're starting to move. They haven't quite got to 8 RPM, but they're moving towards that kind of frequency of rotation. And the reason is that the wind turbines get bigger. The optimum condition for wind turbine is based on the tip speed ratio. And so the tip speed needs to stay the same. So as the wind turbine diameter gets bigger, they tend to turn slower. So if you look at a small wind turbine, you'll notice that it spins very fast. And that's the optimal condition for that wind turbine. As they get bigger, they start to turn slower. What's interesting is the economics of wind turbines says that we actually want to make them bigger and the energy gets cheaper. So even though the rotational frequency is necessarily getting lower, actually, the cost of the energy is actually getting cheaper. And so that would imply that even if low frequencies are down to sort of 8 RPM, doesn't mean the electrical generator will be relatively more expensive. At least in wind turbines, it doesn't make it, as an overall system, less viable. In fact, it makes it more viable because there's gains elsewhere. And so that says to me that whilst it may be a challenge to work at those low frequencies, it's clearly not something which is insurmountable or something which makes it necessarily uneconomic. So there's lots of reasons, or there's these two fundamental reasons. There's a few other ones, but these are two fundamental reasons where you can say lift-based wave energy has apparently a prima facie advantages relative to other technologies. And so, you know, as researchers, we should look at that in more depth. And indeed, what we're able to get funding about just over a year ago now, we got funding from the Horizon 2020 scheme in Europe to work on a 3-year project with 10 partners to investigate wave energy converters based on lift. And it's being led by Queen's University. But what I was very careful with the choice of partners is to make sure that we have a large range of experience. And so what I didn't want to do was to have a lot of people who are experts in hydrodynamics and design a lift-based wave energy converter, which was optimized just for hydrodynamics, but was also optimized from a structural perspective and was considered to be environmentally acceptable and had viable control strategies. So when you look at these partners, Unive Strathclyde are experts in structures, which is why they're included. UCC experts in operation and maintenance. Maynooth experts in control. Wave Energy Centre, Wavegen, experts in environmental impact. Aalborg, experts in cost of energy. Hamburg University experts in numerical modelling, and then LHEEA or ECN are experts in physical modelling. So we tried to get a broad range of people to work together in order to develop this not just one perspective, but an optimization from multiple perspectives. Now, obviously, if we're going to design something, we need to know what we're going to design for. And so we've taken a clear sort of basis design. So we've said we're trying to develop utility scale wave energy converters. It's driven partly by the requirements of Horizon 2020 call, which asked to have an impact on the European energy production, electricity production. But also, I think, you know, if wave energy is going to have a big impact, it's got to start looking at large-scale energy production. But then we should also look at large-scale farms, wave farms. So we're not trying to optimize just for one device. We're thinking about optimizing for a 100 megawatt wave farm. So we're thinking about large-scale device. Now, this has implications in the choice of operation and maintenance. So if you said to someone, we have a single device, how do you design the operation and maintenance? You'll get a different answer than if you say, we've got 20, 30, 50 of these devices, and how do we design the operation and maintenance for that? And so it's important to understand exactly what we're trying to design for. So we're designing for the future. We're not looking at designing something now. And if we're realistic, probably if wave energy based on lift was to become commercially successful, we're looking what would happen in a decade's time, in 10 years' time. And so we want to think about what changes in capabilities may have changed between now and 2031. So how may we be able to use those advances in technology in order to change the design? So that's mindful of that. So that's important to have bear in mind. And then, as I said, the co-design philosophy is critical in the sense that we consider all aspects of design from the start. So often you'll see people will design something from a hydrodynamic perspective. You say, okay, do this and we'll have an optimum power capture, or maximize the power capture. And then when you finally come around to building it, you find the forces are too high, or the generator can't be designed as it's required. And so the philosophy in the LIFT-WET project and how we're developing this technology is consider as far as possible all of the aspects from the start. And so we don't end up designing a system which the environmental people will say that will never be acceptable because of its impact on the ecosystem. So we've made sure we've included that from the start. And so we don't get to the end and say, okay, let's change the design in order to compensate for something, because we actually don't need to make any compensation. We've included it as a consideration design already. And essentially the co-design process which we've developed, essentially goes through this loop here 3 times. So we generate new knowledge. And so, as I said, we've got 6 different types of knowledge. So there's hydrodynamic knowledge, how does the device work, structural knowledge, control knowledge, operational knowledge, environmental knowledge, cost of energy knowledge. So we're sort of generating new knowledge, either comparing it to current technologies or understanding what we have better. And then we apply that to generate some new configurations. And we identify a set of configurations using that knowledge. And then what we want to do is to model that. So we want to understand, well, how well do these configurations based on that knowledge work? And so we have a set of modeling tools, numerical modeling tools, physical modeling in the wave tank, and conceptual modeling, which allow us to analyze that performance, each particular configuration. And then, of course, what we need to do is evaluate those configurations, and we have a set of evaluation tools to do that. And then we evaluate those configurations. Then, of course, we know more about wave energy, and we know more about lift-based wave energy converters, having gone through that whole process. So we then re-feed that knowledge back in, add new bits of knowledge we realized that were missing as we went through that process. And within the LIFT-WET project, the intention is to go through this process 3 times. So we create a set of preliminary configurations, which is what we've done. The second year, we'll generate some what we've called baseline configurations. And in the final year, we'll look at the identification of final configuration, which may be 1 or 2 configurations, which we believe to be the most promising. Now, it's not to say they're the only configurations, but based on the experience or knowledge that we've generated, this is where we think promise lies. So as I said, we've gone through the first loop so far in the first year, and we've identified 13 configurations. We actually identified 17 configurations to start with, and then in very early on in the sort of analysis phase, we got rid of 4 of those configurations because they were unpromising. And we've categorized these configurations based on a number of factors. So number of hydrofoils, the type of rotation, the type of power takeoff that's being used. And so we have a range of different configuration options. Each of these 13 has a unique combination of these. Now, clearly, if you added all of the potential permutations and combinations of these, you would end up with more than 13. But we figured 13 would give us what we feel to be the sufficient knowledge. And then, as I said, we have these evaluation factors which cover all of the things that we feel need to be considered. So we've not only just considered energy capture, which would be the one which many people feel to be the critical, but we've also tried to include, or we've also included, I should say, things like the structural requirements, maintainability. Now, it may be that many of these configurations at this early stage of development have the same level of maintainability or the same level of reliability, but it's in there from the start. So we haven't sort of just assumed they're the same. There's an explicit requirement to evaluate the different configurations, different ideas based on these 16 different evaluation factors. And there's a process within the project to then use these evaluation factors to identify where we should go next. So what I want to do now is just to show you some of the investigations which we've gone through, just to put some details of the type of things we've been looking at and some of the findings that we've got, which are promising. And so there's 4 different aspects. So there's other ones that have been doing within the LIFT-WET project, but I just thought I'd highlight these 4 as being potentially the most interesting. So starting off with the hydrofoil hydrodynamics. So there isn't any sort of easy to use or current tool of looking at how a lift-based wave energy converter will actually work. So what we tried to do is to try and develop a hydrodynamic model which will allow us to point us in the right direction of what we think the performance could be. So we've used sort of actual hydrofoil lift and drag coefficients, used a quasi steady state assumption. So we assume that those aren't affected by the conditions before and after the conditions at any particular moment in time. That may or may not be a reasonable assumption. That's why we're doing the wave tank testing as well, which is planned for April of this year, COVID-19 permitting. And we've also used some far-field relationships to estimate what type of radiation damping is. And as is common with wave energy, we've assumed optimal control at this point in time, just to see, how well things could work. So this is an example of some results for a single type of hydrofoil or single condition. So we've got the non-dimensional radius here of the hydrofoil's rotation. So it's rotation about a point, and that's the radius, how far it's rotating around the point, or half the diameter of rotation, divided by the wave amplitude, because we found that would non-dimensionalize our results. And this is the phase between the wave and the rotation, and we've assumed it's phase locked. So it's moving at the same frequency in the same phase with the wave. And so you can see here the capture width ratio of the device. This is a 24-meter wide device. So it does change slightly as the width of the device changes. But we get a capture width ratio slightly over 1. Now, those people who are familiar with wave energy hydrodynamics will know that that's associated with the point absorber effect. And so that's a possibility, but you can also see that it moves away from that optimum as the radius becomes non-optimal relative to the amplitude of the wave, or indeed the phase varies. But there's a relatively large landing area here. So if the phase varies between plus or minus 30 degrees, and perhaps the radius goes sort of plus or minus 25%, maybe 30%, we're still, if you look here, getting a capture width ratio of about above 0.8. Now, to put that in context, each device is different, but many heaving buoys type devices would probably have a capture width ratio of around about 0.2, 0.3, except for a very narrow bandwidth. And Oyster, a diffraction type device, had a peak capture width ratio just over 0.5. Now, of course, there are assumptions in this which may be overly optimistic, and there's always a tendency in wave energy that as you increase reality, the performance tends to reduce a bit. But what it does show is that there's not a prima facie reason to expect that it's necessarily low. So when we did this analysis, we'd found that the maximum capture width ratio we would get was 0.1. That might be a reason to say, okay, we've done everything we can, we've optimized everything, we've looked at it as best we can, and we're still not getting a very high performance. What it tends to show is that the performance is promising. And indeed, if we look at a range of different wave heights and wave periods, this is for single hydrofoil, so it's different from the model there. It's just a single hydrofoil moving around with a diameter of 16 meters, a span of 24 meters, and a chord of 5 meters. You can see that there's an optimal condition here, around about here at 2 meters and 9 seconds, where we're getting close to 1. And then it moves off away from those optimal conditions because the drag starts to become more significant. It's no longer in its optimal condition. But this is for a fixed diameter. So this is where the design potentially comes in. So if you reduce the diameter, or if you have a variable diameter, then you can start making some of these zeros have positive values. So we can start to increase the range of that capture width ratio. Again, the point is...
Sorry to interrupt, but could I just ask you what length scale you're using for defining the capture width ratio? Is it the span?
It's the span, yes.
Thank you, thank you.
So you can see here that you can start to increase the range of this if you allow your diameter to change. So if you had a design where the diameter could change, you obviously complicate the mechanism, but you increase the capture width ratio, the range where the capture width ratio is greater than 0. And so, you know, this is just an example. It's not meant to be definitive, but it's sort of another example that, okay, there's some promising possibilities that we can move forward with the idea that there isn't anything yet which shows it's not worth investigating any more depth. Another important aspect would be the structural design. So if we look to the structural design, can we make a hydrofoil which would be able to withstand the type of stresses you might get on it? And so here we were looking at a device, or that previous example, looking at a device of 24-meter span. And you can see for the different chord lengths here, even for a chord length of 2 meters, the stresses would still be acceptable. And we could indeed go up to, if it were 5 meters, we're somewhere here. So we could actually have a span. Now, this was based on analysis assuming that there's a box structure here within the hydrofoil. It's potential we could make that wider at the top and bottom to increase its rigidity. But this is a first pass type analysis. So what we're trying to show is that, okay, there's nothing within the structure of the hydrofoil, at least, which is saying this isn't possible, this can't be done. We're trying to do things. If it had come up with, okay, you know, for that size of hydrofoil, it can't be more than 10 meters long, that would be a very different conclusion. So we're starting to find results which are supporting the idea that we need to, that let's say that the idea is not, or is that it remains viable. Just to show, obviously there's some RANS modeling going on, where you can see here the wake from the hydrofoil, from a single hydrofoil. And what we need to do the RANS modeling for is obviously the wave tank modeling, which we're going to do, won't have the right Reynolds number. So what we need to look at is how much the Reynolds number may influence the performance. In most wave energy, we use the fruit scaling, and that works pretty well when we model things in the wave tank. Because we've got a hydrofoil, I'm concerned that what we find in the wave tank actually underpredicts the performance which we may get in full scale. Now, of course, you know, in the old days, we would test something in the wave tank and just multiply it by the fruit scaling and get the power. And that's works relatively well when we look at buoy type devices or flap type devices. But we need to be confident that we're not unfairly assessing our performance. So we're doing some numerical modeling to investigate how reasonable that conclusion will be. Oops, wrong way. So last thing I want to look in a little bit more depth is looking at far field hydrodynamics, and in particular the difference between 2-dimensional and 3-dimensional hydrodynamics. And this really ties up with the point absorber theory and the assumption, which is quite often that a device is simply you can simply model a slice of it and then multiply it by the width. And what we found in flap type devices, and what will be true in this, is that actually that's not the correct way to analyze the results. And the reason is because when the device is moving in heave, and these are far field effects, so it doesn't really matter how that interaction occurs, you get a different radiation pattern, different way the waves are radiated than when it's interacting in surge. And the consequence of that is that when the device is interacting during the surge motion, the power capture is twice what it would be when it's interacting in the heave direction. So let's see what the implication of that is. So when we're in deep water, we have power is force times velocity. I'm sure you're all familiar with that. And the lift force is a function of velocity. So hydrofoils typically, or aerofoils, the lift force depends on the velocity. And in deep water, the horizontal velocity is the same as the vertical velocity. So if we then apply that to the above equation, we've got a similar lift force because the velocities are similar, but we have a different power because the power in surge is up to twice the power in heave. And so therefore, we're going to end up with a different optimum motions in heave and surge. And that implies elliptical motion. And if you look at the level of ellipticity, assume in deep water, in 2D assumption, we get circular motion, but what you find is that as you start to get, the device gets smaller, you get more and more elliptical motion in order to extract the maximum amount of power. And here we have non-dimensional span. So a non-dimensional span of 3 is about half a wavelength. So in a 10-second wave, this would be 75 meters. So if we go back to the 24 meter span, we're right here where the optimum hydrodynamics would imply we need to move twice as much in the surge motion as we do in the heave motion. So let's look at shallow water. So here we start with the same power as force times velocity, and lift force is a function of velocity. But now the horizontal velocity is no longer the same as the vertical velocity. Horizontal velocity is larger than the vertical velocity. And so we have a different lift force and a different maximum power capture. So we have different lift forces because the velocities are different. And so if we combine those appropriately, we can actually have the same optimal motion, which would imply circular motion. Now, of course, in real waves, there's going to be deviations from that, but we're closer, we can remain closer to the optimum requirements if we move into shallow water. So the question is, what does that mean? What do we mean by shallow water? So here we've got water depth against wave period, and we want to get, depending on the width of the device, we want to get somewhere between 1.5 and 2. So if we looked here at wave period of 10 seconds, we want to get between 1.5 and 2. We're looking at depth somewhere between 22 and maybe 35 meters of water depth. And that's a nice water depth in the sense we're outside, or we can be outside the region where waves are breaking, which tend to occur closer to shore, but not so deep that it starts to make the structure very expensive if we're going to use the seabed as a reaction source. So it's an encouraging result, not only because we can potentially in 30 meters of water improve the power performance compared to deeper water, we also potentially reduce the structural requirements. And I also wanted to make clear that those aren't the only things that are going on in the project. We're also looking at sort of control, environmental impact, operation and maintenance and cost of energy. So those are other ongoing investigations within the project. So let's have a look at the primary findings that we've made in the project so far. So we have a promising power capture. At least there's nothing at the moment which is showing the power capture would be necessarily too low. I didn't show you this, but there's been environmental impact assessment which shows that there's nothing special about this type of technology which would make it significantly more problematic than other types of wave energy device. We've seen that the structural design appears to be viable, and there's nothing else that we've identified within any of the findings that say there's a fundamental issue with lift-based wave energy converters, which says this isn't a concept which we should dismiss. Indeed, most of the findings shown this is a concept we should look at in more depth. Now, I tried to do the next slide programmatically, and I like to say this is where we are. So we have a rough sketch of the sort of what we need to know. But what we really need to know is a larger area. We need to know more about the technology. And then once we've sort of know more about lift-based wave energy converters, we need to start coloring that in. We need to start increasing our understanding so that we have a more detailed understanding. And then hopefully we'll get to the end where we have a nice clear picture of how lift-based wave energy converters should be designed. And, you know, let's hope that it does show the viable alternative, let's say, because I don't want to dismiss other technologies, but another viable alternative for wave energy. So let's go back to our lift-based knowledge, lift-based wave energy converter knowledge, and see what we've been able to do is to start to fill in some details about what we need to know. So we need to know what's the bandwidth, how do hydrofoils interact? So if we've got 1 or 2 or 4, how will they interact? What kind of near field effects might we need to consider? You know, how should it, what's the optimum path? You know, this is a little bit started when we looked at water depth, but how does the variability, the irregularity of the waves affect our optimum path? How should we control the reactive energy? What other control parameters should we use? Which ones are worth it? How should the hydrofoil profile be? Do we want a thin profile, a fat profile? You know, what type of characteristics we want it? What sort of size should it be? And obviously, you know, in terms of commercial potential, what issues do we have in terms of survivability, the O&M strategy, environmental impact? So starting to flesh out those questions which need to be answered. And I'll come back to this slide again with a slightly different picture, but the same quotes, because when we start in this, as I say, new ideas are often considered crazy ideas until the idea succeeds. And when it succeeds, everybody forgets the fact that they said it was a crazy idea, and in fact, they can sometimes claim that they've always thought it was a good idea. And we shouldn't run away from that idea. Don't run away from the fact that people think these are bad ideas. Ask people. Well, my view is always ask people to say whether they feel why they think the idea is bad, and perhaps they have good points, and those can be addressed. The last slide here is I wanted to sort of just say that this research, the LIFWET project, is an open project in the sense that we're encouraging collaboration. All of the data which is being generated within the project will be available as open access data, and it'll be available for anybody to use. And all the deliverables will be on the website. So there's a LIFWET website, and we're happy to share all those deliverables with people. When COVID-19 finally passes the world by and we can have a more regular life, I'm very keen personally for research visits. So if you wanted for me to visit, or someone else, or you wanted to come and visit one of the other research teams, then that's actively encouraged. And indeed, if you started to work on lift-based wave energy converters and you wanted to look at the potential for a joint publication or build on some work that we're doing within the LIFWET project, then that would be also something which we're very keen to encourage. My view is that as researchers, collaborations are beneficial. There is so much. When we compare the amount of work that's been done on lift-based wave energy converters, if you compare the tens of research papers which have been written compared to the thousands that have been written in other parts of wave energy, then you can see I don't think we need to be protective about the research we're doing. There's plenty of research required, and I encourage everybody to be involved, or if they want to be involved and they see an area which they can contribute, then I encourage you to get involved. And if you want anything from the LIFWET project, then please let us know. and we'll help as much as we can. And also, I don't want you to think that the ideas that we've generated in LIFWEC are extensive. Obviously, it's a project which is designed to try and identify a promising technology. But there may be ideas that you have, which you go, actually, I've thought of a different way of doing that, and actually, I think it's better than what the LIFWEC project's doing. That's something I would encourage, because I'm not going to say this is going to come up with the best idea. What I really want to do is generate the knowledge and put the knowledge in context, which then other people can build on. So a couple of contacts. There's my email there and the LIFWEC website, which I encourage you to visit if you're interested more. And thank you for your attention. And we don't have that long. I'm available to stay for as long as there are questions. But I'll hand back to George to facilitate the session.
Thank you, Matt. So what I'm doing now is also for everybody to have the LIFWEC website directly. I'm going to put it in the chat. Thank you. That's a new and interesting concept, and we all need it. So if there are any questions, please do so. I do have one question from a participant while you were giving the chat. It's more into the integrated breakwater of WECs, but let's start off with something more relevant to the LIFWEC. So, Professor Bingham, yeah.
Thank you. Thank you, Matt, for really nice, very interesting presentation. I think this is a very exciting idea. I remember back in the mid-90s when Pinkster and Hermans from Delft presented this idea at a water waves workshop that I attended. And at that time, they were looking at a single foil. And I know that Pinkster, talking to him subsequently, he was very keen on the idea that you had an asymmetric device so that it could be passive and self-starting. And so I was just wondering, I mean, I can see that the Autargis and subsequent developments on this PsycWEC project, they have adopted a two blade model, and that requires control. So I just wonder what your thoughts are on what is the optimum number of blades for this kind of device.
I mean, I suppose the quick answer is that's to be decided, and I think one of the keys is to make sure that when we review the two different options, and let's just say the two different options are single and two bladed, two hydrofoil devices, as you say, the advantages of self-starting or any other advantages associated with a single hydrofoil need to be compared against the advantages of the dual hydrofoil. Now, it may be that that the advantage differs depending on circumstances. And so when you look at, I mean, there have been single foil wind turbines designed, you know, so you don't need wind turbines, but I imagine they haven't been developed because of the oscillating load, the imbalance in the load. Whereas the three-bladed turbine tends to be better balanced. Now, and this is where you need to consider not only the hydrodynamics and the such like, it's also the cost of the construction and whether the loads on the bearings would be imbalanced by the gain or potential gain associated with self-starting. So but that's one of the things which I think we need to identify. So one of the challenges I always find is that in many cases, people have a perception that this will be better because of their previous experiences. And I think what needs to be done is to investigate both fairly and reasonably, and then identify why one particular technology is more promising. And I'll come back to wind turbines. When I started in wave energy back in 1987, I asked my supervisor, my undergraduate degree supervisor, what part of renewable energy. I wanted to work in renewable energy. And he said, well, wind turbines will never be more than about 400 kilowatts because of stress loads on the wind turbine blades. And so therefore go into wave energy where you can get bigger machines. And that was true until they started making, so at that time blades were made out of steel, and the fatigue of steel is very poor. And so that truth, which was the truth if you're going to make wind turbine blades out of steel, suddenly changed when you could move to composites. So the question is, if you like, the optimum doesn't necessarily stay fixed and rigid. It may be that at some point in time, due to the technology available, the need for self-darting is required, in which case you may find that a single blade is the optimum. Then later on, you may find that through some sorts of intelligent sort of control, you're able to get them to start without too much loss of energy. So I know I've sort of sidestepped that answer, but I think we do need to base these base everything on information, on knowledge, and also be aware that knowledge can change as a result of further research and changes in potential technologies that can be used.
Oh, thank you. I don't think you sidestepped it at all. I think that's an excellent answer. And I also would just like to commend the attitude you're taking with this project to be open to collaboration and things like that. I think that's fantastic.
Good, thank you. Thank you.
So, Matt, we do have another question from the chat, not related exactly to the lift concept, more on wake integrated breakwaters. What do you think is the scope for protecting the coastline through attenuating the wave energy? What do you think are the operational limits, and how many years does it take normally for a wake to break even? So I know this is not totally on lift wake, but you've got more than...
No, I can't. Okay.
Yeah. So you can give a rough estimate,
yeah. I could do my best to answer some of those questions. I think the last question about cost is it's really too early to know how much these things cost. So break even is beyond the scope, and I think it's sort of, until we've started to build hundreds of these devices or hundreds of wave energy devices, it's very hard to know with any kind of certainty where we are. No one would have thought, even 10 years ago, I would suggest no one could imagine how cheap offshore wind has become. And so if you ask someone 10 years ago what potential is there for offshore wind, they'd have probably gone, well, there's a few niche locations where you can make it cheaper than the local grid. Now, offshore wind is starting to significantly challenge in all types of circumstances. And so we have to be careful about using the sort of what we know now and assuming that somehow it's a solid piece of image. With coastal protection, I think there are two things that, if you're talking about putting things in a breakwater, which already exists, or you're going to build the breakwater anyway, then what you're looking at is the marginal costs of including the wave energy. Now, that could actually help with the breakwater design. I know there's been some research on oscillating water columns built into breakwaters where they feel that the loads on the breakwater have been reduced because of the change in phase between the front wall of the oscillating water column and the back wall of the oscillating water column. So there's potential to reduce the construction cost, but also there's obviously the potential to increase or to produce a side product of energy, and because in oscillating water columns, especially, most of the cost is in the construction of the structure. That seems to be quite a potentially interesting possibility. If you're looking at building coastal protection, which is only sort of there as a coastal protection, so you'd have a device. Now, wave energy converters extract energy from the waves, and so there's been an argument that's been proposed that says, well, okay, let's build lots of wave energy converters, a submerged wave energy converter, which isn't a breakwater, so it actively extracts the energy. And then we can protect the coastline as a result of that. Now, there's two issues there. Is the ability for the wave energy converter to extract energy tends to be frequency dependent. So certain frequencies will pass through that non-solid boundary to different degrees. And one of the questions is, how will that change in frequency affect any literal processes of what you're trying to protect. And indeed, there's interesting where they've looked at detached breakwaters with coastal protection, and they've often found that they aggravate the situation more than they solve it. The other, and sort of related to that, is that most wave energy converters become ineffective or largely ineffective in the largest sea states. And if the coastal protection is you're trying to protect from the largest sea states, it's unlikely that a solid barrier, in my opinion, will actually be effective. And so if you're trying to protect the coast in order to reduce the littoral process, some sort of erosion which occurs due to continually large number of small waves, then you could use wave energy as a protection. If you're trying to protect it from large events, I would suspect that a non-physical barrier type wave energy converter is unlikely to be effective. But that's, going back to my usual thing, that's my perception. It's a prejudice. I don't have evidence to base that on. But that's my view anyway.
Thank you. Thank you, Matt. Yeah.
One last question, I think, from Plithos, I think.
Thank you. I had a question because a lot of this concept reminded me of some tidal turbines that I've seen. And one of them is from a company called Kepler Energy. It was spun out of the University of Oxford, Department of Engineering Science. And they have a transverse horizontal axis water turbine. So that's effectively a Gorlov turbine, so a helical vertical axis turbine that's being turned onto its side to take the tidal flows and make electricity out of that. So have you cross-pollinated or collaborated with tidal energy at all?
Yeah, so we have, there's a research group at Queen's University, or our research group, I should say. There's another research team who's looking at a horizontal axis cross-flow turbine. And I think there is definitely some similarities, but there are also some significant dissimilarities. So it is something we've looked at, and I think the guys at Hamburg University who are doing numerical modeling have also done some modeling in that area. I think one of the issues is when you have a unidirectional flow, what happens is in a sort of a Gorlov type turbine, you get the wake from the sort of first turbine then impacting on the second turbine. But when you're going around, when the water particles are going around in a circle, it's not obvious to me that the wake actually reaches to the far side of your turbine. And so you're actually sort of interacting the effect of the multiple blades or the effect of the rotation, which would in a sort of a unidirectional flow mean you're passing through a wake, won't necessarily be the same as in a wave energy device. But it is something which we've sort of looked at, and indeed the numerical modelers have looked at in more depth. Because I suppose the impact is what would the wake, how will that have an effect? There's obviously structural things as well. And indeed, I think there's a project at Cork University, which I'm very interested in, where they've looked at a submersible generator. And so some of the technology would definitely be transferable. So it is something we're aware of, but I mean, there's always a chance to learn more. So if there's things that you think would be particularly interesting, I'm very pleased to hear what you think.
Or if I could just add to that quickly, John DeBerry out of Stanford found that if you have counter-rotating vertical axis wind turbines, so one going in a clockwise and another going in a counterclockwise, you can create a farm that does quite well with that wake. So you can have them quite closely spaced, you can have them quite close together, and they have almost a constructive interference pattern. So it's based on biomimicry of how fish move in water as well.
Yeah, it's interesting. I worked on a constantly rotating turbine for LIMPET plant because in unidirectional flow, in relatively constant unidirectional flow, the performance was increased by about 10%. So if you looked at the LIMPET plant, it was originally installed with a contra-rotating turbine. When we actually put it in the plant and measured the performance, we found the performance was actually quite a bit less than a unidirectional turbine. And when we investigate that in more depth, we found that when we talked to the guys who were doing the testing in the laboratory, they said, oh yes, we noticed that it took a while for it to settle down into the right condition in order to get those higher power captures. And so to find that right flow regime is was actually took a while to set up and settle. And of course, in irregular flow, in an irregular wave, you found that never actually reached that stable condition. And so whilst I guess I'm not disagreeing with you, but quite often there is a fair difference between contra-rotating and, sorry, I should say unidirectional flow and this sort of circular wave type flow that occurs.
Thank you.